Hi, everyone. My name is Tim Rupert from the University of California, Irvine, and I'm here to talk to you about how we can change the structure of interfaces and dislocations to control mechanical response. Now, our interest in this topic is really rooted in the idea that defects themselves can be described as a thermodynamically equilibrium state. A lot of this work comes from the great successes in trying to stabilize nanocrystalline materials, where you can think about the grain interior and the grain boundary itself as different structural states. And if you think about this and extend it a little bit, you can imagine having different grain boundary states be possible. Just to show an example, in this case, Frolov and coworkers are looking at grain boundary excess as a function of grain composition. What they were seeing is that silver goes to this copper grain boundary, first in a monolayer, but then as you increase the composition, eventually you have a transition to a bilayer structure. More complex structures can be imagined. So you can imagine having a fully amorphous or disordered film at the grain boundary. And in fact, people like John Luo at UCSD have done beautiful work to try to build on traditional phase diagrams and show what sort of thickness of these amorphous complexions you would expect. Now, at the end of my talk, I'm going to show you a few results where we're showing that dislocations can also have complexions because they have variations in their local structure and stress. So in terms of interfacial complexions, when I'm talking about that, I'm mainly going to be talking about nanocrystalline alloys. We started in this area by working with nanocrystalline copper zirconium. The idea is pretty simple. You can do something like ball milling, make a nanocrystalline alloy. You heat up to a high temperature, in this case, below but near the melting temperature of the alloy. This gives you enough thermal energy for segregation. And in our case, we actually get pre-melting or formation of these amorphous complexions at the boundary. Now, if you take these materials and you rapidly cool them, in this case, we have powders in a vial, we drop it in ice water. What you'll see when you go and do TEM of the interfacial structure is sometimes your grain boundaries have this amorphous structure, amorphous complexion there. In contrast, if you slowly cool down your sample, you'll end up doing your TEM experiment. You'll find that you never find amorphous films. Instead, all the grain boundaries are these ordered, sort of boring structures. Now, it turns out that this is beneficial for many properties. We're really interested in it because it affects the mechanical behavior. So for example, nanocrystalline copper zirconium with ordered grain boundaries is very strong, but very brittle. In contrast, if we add these amorphous complexions, we find that it's very ductile and actually a little bit stronger. So you're getting the best of both worlds. And we've also used this for other things. For example, we found that these amorphous complexions can help densification of these powder materials into bulk pieces, and also that these amorphous complexions can increase the radiation tolerance of our samples. In terms of mechanisms, we dug into this a few years ago with molecular dynamics and tried to understand how dislocations that are incoming and need to be absorbed by an interface can be affected by the presence of an amorphous complexion. The basic story is pretty simple. You need to accommodate that plastic strain that's coming in. And in amorphous structure, you can have activation of shear transformation zones. And in this case, these darker colors are coming from local plastic strains that are being shared within that amorphous phase. There's lots of sort of evidence coming out that this is a reasonable interpretation. On the top right here, I'm showing you an example. These people made aluminum alloys with amorphous films at the grain boundaries. They found that this material was stronger and more deformable than a metallic glass or a nanocrystalline alloy. And in fact, their mechanistic explanation was quite reminiscent of those earlier simulations. A dislocation comes in, there's a shear transformation zone at the boundary, and that accommodates that deformation. On the bottom right is showing a similar type of idea. In this case, the grain interior is a multi-principal element alloy, but the net effect is the same thing. The amorphous interfaces end up being beneficial for having homogeneous deformation. And finally, this is showing an example from a chemically ordered set of lattices where a disordered interfacial layer can give you this best of both worlds, increase in strength and increase in uniform elongation. So for what I'm going to tell you about these amorphous grain boundary complexions, I would first want to think about how we can try to optimize the complexion content. That can mean many things, but for example, it could mean that we want thicker amorphous films. Maybe we want a larger fraction of the boundaries transformed or more stable amorphous films. And I'll talk about two things. We're going to look at grain boundary chemistry and also processing in terms of quenching rate. So for looking at grain boundary chemistry, we can hypothesize that if you increase the chemical complexity, maybe you can get these thicker amorphous films. So we can go from the copper zirconium binary alloy to a copper zirconium hafnium ternary alloy. We find that we get segregation to most of the boundaries. But more importantly, if we go in and we measure all of the amorphous films in our microstructure, we can find them all, and we can, as many as we can see, and we can measure their thickness and then make a plot that's a cumulative distribution function of that amorphous intergranular film thickness. What we find is that the binary curve is shown here in the red, and the ternary curve is shown here in the blue. Now, the point is that this curve is pushed to the right, which means we see thicker amorphous complexions in the ternary sample. We can take this concept and go even more extreme. We can go to a 5-component system. Here we're showing 3 different examples. The XRD grain size all stay nanocrystalline after up to a week at a very high temperature. So what we're going to do is look more closely at this copper, zirconium, hafnium, niobium, titanium material. Now, one thing to point out is that although we have 5 elements in our system, we actually don't end up having 5 elements at the grain boundary. So in this processing route, we sometimes get carbides in our sample. And in fact, in this case, all the hafnium that we wanted to go to the grain boundary ends up getting sucked up by the carbide. So this is an example showing at the grain boundary, we have copper, niobium, titanium, and zirconium. So we have 4 elements there. More importantly, what we can do is again, go measure the distribution of the amorphous complexions. We find that this curve is pushed further to the right. So we have a very consistent observation. As we go from 2 to 3 to 4 elements at the boundary, we get thicker and thicker amorphous complexions. So increasing that chemical complexity does increase the thickness of those amorphous complexions. To look at processing rate, we can think about doing controlled quenching experiments. So these amorphous complexions are the high temperature structure that's in equilibrium. And as we cool, we risk losing some of that. So the way we want to test this is we'll take some of those bulk pieces I mentioned, and we'll, instead of just dropping them in a quenching liquid, sort of uncontrolled, what we'll do is we'll take and we'll put it on a heat sink. And the idea here is this aluminum block, which is cooled by liquid nitrogen, is going to be pulling the heat out of that sample. And the bottom of this little pellet is going to cool very quickly, and the top is going to cool much more slowly. We can go and model this, try to understand the heat transfer a little bit. I'm not going to talk too much about these details. You're welcome to pause and look at them, but the main point is that we can get multiple orders of magnitude variations in the cooling rates in these regions. Most interesting from a material science perspective is that when we look at the samples that are very fast, quickly quenched, we end up seeing lots of boundaries are amorphous and they seem to be very thick. This is just showing one example grain. There's multiple amorphous complexions around the outside, showing a zoomed in image and then a schematic marking each of these as either amorphous or ordered. So if we go and we measure these distributions of complexion thickness, we can start to see some differences between the binary and the ternary. The binary shows curves which change as a function of the location within the sample, which is really as a function of the cooling rate. So if we cool very fast, we get thicker amorphous complexions than if we cool slowly. In contrast, the ternary sample shows a complexion thickness distribution which is invariant to that cooling rate. And that tells us that we're really not seeing any transitions from that high temperature structure. We can kind of visualize this by going and looking at a schematic TTT diagram. So the high temperature state, the amorphous complexions, want to transition back to ordered grain boundaries, the low temperature state. And the binary seems to cross into this transition region, and some of the boundaries go back to being ordered. In contrast, the ternary does not, and you get this invariant sort of distribution. You can imagine or understand this a little bit better by looking at sort of an analogous example in the metallic glass type of area. So if you look at a pure metal, we could take a pure metal from the liquid state and make a glassy solid, but we'd have to quench down very, very fast. In contrast, a bulk metallic glass has the right composition that we can quench much slower, more reasonable rates, and still get a glassy solid. So one thing we can do is try to estimate the difference between the stability of this binary and ternary material. So one thing we can do is say that, well, this fast quench distribution falls right on top of the ternary. So that seems to be representative of the high temperature structure. And we can say that this fast quench was just barely fast enough to freeze in the high temperature structure in the binary, which means that the nose of this transition region should fall right near there. In contrast, we can make a sort of conservative estimation and say, well, the slow quenched case for the ternary falls in the same right over top the other curves. But let's say that it was just barely fast enough. If we did it any slower, we would end up having transitions back to these ordered boundaries. So then we can position the nose of that ternary system. The main idea is that we want to get a rough estimate, and we can do that by looking and plotting some constant cooling curves that hit those same points. And we can estimate that we can cool the ternary alloy about 1,000 times slower and still freeze in that high temperature structure. Another thing we've been doing is trying to really understand more about the interplay of all the different complexion types you have within your sample. So I mentioned that there's these amorphous complexions, but not all the boundaries are amorphous. So whenever I was showing you one of those distributions, I was showing you all these measurements of the amorphous complexion thickness. But the information we didn't have from those experiments were how many boundaries are ordered and what's the variation in thickness of those interfaces. That's very hard to get experimentally. So we can't answer something which seems simple, like what fraction of the boundaries are amorphous. So to try to extract out some of this data, we've been running complementary atomistic simulations. On the top here, we're showing polycrystalline samples, pure copper and copper zirconium at 900 K. The bottom here is just demonstrating that the grain structure doesn't evolve much just from the doping process. But more importantly, we can test different temperatures. So for example, we can compare the 900 K and 1050 K samples for the alloys and end up seeing how the complexion networks differ. On the left here, we're showing all kinds of data for grain boundary thickness for these various samples. The shaded gray region is where all of the data from the pure copper falls. It's very boring. There's not much variation. What you can see is for the alloyed samples that you get some points that fall above those bounds. And these are the interfaces which have transformed to become amorphous complexions. Okay. Now, one other thing you notice is that some boundaries have moved below those bounds. It turns out those are just annealing twins which have formed inside of some of the grains. These are copper alloys after all. So those can be sort of disregarded. But we can look at that distribution of grain boundary thickness, and we can now see on the left at the low values, these are those ordered grain boundaries that we were missing in the experiments. And anything beyond what you see in the pure copper, we can hypothesize that these are these amorphous complexions. And you can go back and check, and it turns out that they do have an amorphous structure. What's nice about that is it lets us start to put some numbers on the amount of transformation. So we can say that 6% of the boundaries have become amorphous at 900K, 23% have become amorphous at 1050K, and things like that. Just as a sanity check, we can just plot the right side of these distributions for these simulated data sets against one of our experiments and see that the shapes sort of look relatively the same. Now, they don't look exactly the same, but we wouldn't expect them to. The experiment is at a higher temperature and higher composition. In my last few minutes, I want to talk about linear complexions. The idea is that dislocations can also have some of these nanoscale phases. The motivation for this comes from some very beautiful experiments from a group in Germany where they were able to show that along dislocation lines, you got heavy segregation. And when they looked and did diffraction of these regions, they found that this is an iron-based material. This local structure changed from BCC to FCC. Now, we've been studying this with atomistic modeling tools, originally looking at the formation of these nanoscale phases along dislocation lines and their structure, and even looking at things like the phase transformations and phase diagrams for along those dislocation lines. But I want to talk to you about the mechanics. So we can think about and compare what happens to a simple dislocation simulation as I stress this and force those dislocations to move for a solid solution, or a sample where we've allowed those linear complexions to nucleate out. And what we find is that the sample with the linear complexions is much stronger, but more importantly, the mechanism by which the dislocation moves is very different. For the solid solution, this is showing the 3D view, but let's look at the 2D view. As we go from different times, that dislocation moves as a line, kind of how you would expect. In contrast, for the linear complexion sample, the dislocations get caught up with those complexions and have to bow out and get past those obstacles. What's interesting is those obstacles are not in the slip plane. This is not a classical particle. This particle is actually above the slip plane and the dislocation is moving underneath it. Now, the reason it's stuck there is that's the thermodynamically stable state. It's happy in that location. Now, finally, we see that if we look at the sample, we get some undulations in the amount of B2 and L10 atoms in the structure. And that's just representative that as this dislocation moves away from that linear complexion, those L10, those green atoms, transform back to a B2 structure. So the structure of that complexion and the dislocation itself are related. So with that, I'll leave you with some basic take-home points. Amorphous complexions can be promoted by both alloy choice and processing parameter. Chemical complexity and rapid quenching enable you to freeze in those high temperature structures. And finally, that we can also get complexions near dislocations. Thank you very much for your time.